Hi, I'm Charan, and I'm here to present my work, just Stutter, benchmarking Whisper's performance disparities on different stuttering patterns. Both me and the other author, Shaomei, are both people who stutter, and that helped inform our work. So stuttering is quite common. It affects around 1% of the world population, which is over 70 million people. And most stuttering falls into one of 5 disfluency categories. So first, we have sound repetitions, such as playing music. We have whole word repetitions, my name is, or prolongations, play music where it's dragged out, blocks or stops where you get stuck, my name is Charan, and interjections, where this is my dog, where interjections like or are excessively added into the speech in order to often add a block or other moment of disfluency. So for ASR models, in essence, they take in speech, they run it through an acoustic and a language model, and then spit out an output transcription. However, the problem is these models are overwhelmingly trained on fluent speech. And for people who stutter, it has large negative impacts. Higher research shows on average a 4 to 10 times higher word error rate for people who stutter. Oftentimes, people who stutter are cut off mid-sentence, as this system mistakes a pause for the end of a sentence, or it misunderstands their intent, writing down the wrong statement or instruction. And these moments are incredibly frustrating. And oftentimes, most people who stutter avoid using these models, going out of their way to try and type or speak with a human being instead. So for our project, we used the stuttering events and podcast SCP-28K dataset from Apple. Has 28,000 short clips from podcasts, each 3 seconds long, and the podcasts are ones which have people who stutter. It's annotated by 3 independent labelers who label for the presence of a disfluency type. And the strength of this data set is that it's publicly available, so anyone can use it. It's quite large in scale with 28,000 clips, and importantly, it has authentic organic conversations. It's not a script or an interview, but it's an organic conversation, often between 2 people. And that affects the way people stutter because it affects their mindset and their stress levels. However, this data set, its cons are that it does not have transcriptions. It just has the labels for whether a disfluency is there or not. It does not have the actual text. And this means that we had to manually transcribe the data ourselves. Additionally, there's extremely low inter-rater agreement. Between the 3 labelers, they often disagree with each other. This is largely due to the subtlety of stuttering. To accurately identify a stutter, it often takes paying attention to breathing, voice strain, or the tone. And this is often hard for fluent speakers, which the annotators were. Only after it takes quite a bit of time around a person who stutters or stuttered speech to understand these subtle cues that identify as stutter. Often, one error that we commonly saw was mistaking a stuttering prolongation with the fluent one. For example, a dragged out is often not a stutter, it's just a person thinking. But sometimes it is a stutter. And to identify that, the viewer has to pay close attention. And that didn't happen in this data. When annotating SCP-28K, we prioritize clips with unanimous agreement between all three labelers to identify the highest quality data and the ones with the various disfluencies. In transcription, we had two types: verbatim, which preserves the disfluent moments, and the semantic ones, which omit the disfluencies. And it is important that we keep the verbatim one because it preserves the authenticity and exact word-for-word transcription of what was said. And we often see this verbatim transcription missing from existing stuttering data sets. In our process, we have to relabel over 25% of the types in our sample, which shows the high level of error in the original labels. In total, we had 2,621 transcribed clips with the breakdown that you can see there. So for benchmarking Whisper, the reason we use Whisper is that first, it's open source, second, it's state-of-the-art and it performs extremely well on current benchmarks, and third, it's extremely popular. It's widely used in the real world for many commercial applications, so our results would have a real world relevance. For the process, we ran transcription through OpenAI's API for Whisper Large v2 and through Hugging Face for Whisper Large v3. And then we compared both verbatim and semantic outputs, so we wanted to see if Whisper only focused on the meaning or actually transcribed what was said. The metrics that we use were word error rate to quantify syntax differences, and BERT, bidirectional encoder representations from transformers to identify semantic differences. Here are our overall results. We see a persistent gap between stuttered and fluent speech across all metrics and models. Whisper does, and it does worse across the board. And we also see an improvement from V2 to V3, but still a gap persists. One thing that we also notice is that there's a smaller gap for verbatim transcriptions than the semantic ones. And this is probably due to the short nature of the 3-second clips, which mean the model does not have time to understand context. Additionally, we noticed that while V3 got better, it did lose some of the ability to identify the disfluency. Instead of transcribing just, it would just write just. And this, while it captures the intended meaning, does not authentically represent what was said. And so gains in semantic accuracy came at the cost of speech authenticity. For this, when we break it down by odd type, we can see that the models consistently did worse on sound repetition, with the word error rate 13 to 25% higher than others uttering types, and more than double the fluent word error rate. We can also see that Whisper handles interjections and word repetitions better, and perhaps this is due to the fact that those disfluencies occur more in fluent speech as well. But though we do also notice that V3 got worse in word repetition handling, which ties into what I said before about how V3 focuses on intended meaning rather than authentically representing the speech. And this focus on intended meaning rather than authenticity is not a good thing, as these models are meant to do their job and transcribe audio. And so by getting rid of disfluencies or repeated words, it is not an authentic transcription of what exactly was said. Here, we also evaluated the hallucination rate, which is where an ASR model outputs content not in the audio at all. And we do this by leveraging the fact that hallucinations are inherently non-deterministic. So we would run Whisper twice on the same thing, and then we compare these transcriptions to each other. And since hallucinations are random, if we see a big gap between these two transcriptions, if we see a gap between these two transcriptions, we can flag it as a potential hallucination. And so we would rank the outputs by this discrepancy and then manually identify potential, manually go through them to identify the heuristic to identify hallucinations. Here are our hallucination rate results, and we can see that V2, once again, a big gap between stuttered and fluent speech. V2 hallucinated on 14% of stuttered clips versus only 3% of fluent ones. While V3 improved a lot, only a 2.9% rate for stuttered and 0.9 for fluent, we still see a big gap. Additionally, we see how sound repetitions are responsible for trigger the most hallucinations. And we also notice qualitatively that in its hallucinations, V2 often added long, irrelevant chunks of gibberish, while V3 mostly added just sentence completions, which is still completely incorrect and not in the audio at all, but it's less random or noticeable. We also broke down the hallucination categories by harm type, like the work in Haneke's paper. And some categories that we saw were perpetuation of violence, where it would randomly add words like fight, false authority, where it declares facts and takes credit, or inaccurate associations, where it just has a random topic. We also noticed a new category here of a degrading onomatopoeia, like oink 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 or blah blah blah. And these categories are important because they can be extremely offensive or damaging. When we compare V2 and V3, we see how some categories like false authority went away, but overall, most of these still continue. In conclusion, we see persistent gaps between stuttered and fluent speech for ASR performance. Whisper improves from V2 to V3, but the gap still persists. And we also see a regression in verbatim accuracy as the model focuses more on the intended speech rather than authentically transcribing what was said. And hallucinations remain a risk. One of the limitations of our work is that the 3-second clips in SCP-28K are inherently hard to transcribe for both human and ASR. In the future, we hope to benchmark on longer length, on variable length, multilingual data sets, benchmark other ASR models, and also develop models that perform better for stuttered speech. All the code and data set are open source, and we invite you to use it in your work. Thank you for listening.
Do we have questions from the audience?